Hello folks, Professor Fiore here, and today we've got some fun things to do. What I'm going to call network fun. Basically, this is an interesting challenge of a circuit. It's a test of how well you understand circuit analysis, how you can sort of logically deduce results. And I'm going to tell you right up front, if this kind of freaks you out, don't worry about it. I'll bet I could give this problem to any number of professional engineers, and a whole bunch of them would be stumped by it. So, without further ado, how's this for an interesting circuit? We have basically a huge network here. Well, maybe huge is not the right word, but there's 14 total resistors. They're all 1K. And what I want to know is, what's the voltage on this final one out here? What's V out? Got a 10-volt source, right? Now, how many different ways can you solve this? I mean, it's certainly solvable, right? There's no question about that. But how do we go about doing it? You can't do basic series parallel simplifications because with this sort of configuration, it doesn't get any simpler than this. Right? You can't say that R1 is in series with R2 because here's R10. You can't say R2 is in parallel with R5 because, again, R10 and R11 are in the way. There's really nothing you can do here as far as that is concerned. You can't use things like, say, superposition. You only got one source. Thevenizing theorem isn't going to help you. Source conversions aren't going to help you. So what do? Right? Well, you would probably just say, well, I could do a mesh analysis on here, right? It's kind of big though. If you think about a mesh, you got 1, 2, 3, 4, 5, 6, plus this outer one is 7 loops. If you did a nodal, you've got one node here, and then the 6 in the middle plus the ground, right? So that's essentially 8 nodes you're going to have to figure out. Now, granted, in both cases, you're going to have a lot of zero terms. So your matrix winds up being kind of sparse, and that simplifies things. It makes the grind through it a little bit easier. But I want to look at something a little bit different, right? It turns out if you think about this circuit and some of the things that must be true in it, it's actually quite easy to figure out the value. It's actually quite straightforward. You won't even need a calculator to figure it out, all right? Does that sound cool? All right, so at this point, you might want to just stop the video and say, hey, let me get out a pad and a pen, and I'm just going to kind of noodle around on here and see what I can figure out. All right? So you can always come back later, right? The beauty of video. Now, on the other hand, maybe you're compulsively curious and you just want to sit here and watch and see what's going to happen. Okay? So, what do you need? A hint. Yes, a hint. So what I'm going to do is I'm going to look at a piece of this. I'm going to look at a chunk, right? This little chunk right up here, which of course would be the same as this chunk, which would be the same as this chunk, which would be the same as this chunk, right? But just that little configuration of 5 resistors, all right? My claim in this circuit is that VA must be the same as VB. And as a consequence, the currents through R20, R21, R22, and R23 must all be the same. Why is that the case? Well, this is a symmetrical circuit, right? If you rotated it around the horizontal axis, you'd basically be swapping R22 and R20, R23 and R21. Well, they're all 1Ks. Does it matter if this one's up here and this one's down here? No, it doesn't. So, the bottom line is it must be the case that this current is the same as this current. Well, if these two currents are the same, then the voltage drops across them must be the same. And consequently, that drop from the supply, giving you VA, must be the same as this drop off of the supply, giving you VB. So VA and VB must be the same size. right? Whatever it works out to voltage-wise, right? Whatever this voltage is, that's what this voltage is. And if that's the case, then the differential voltage, in other words, VA minus VB, sitting across R24, that voltage is 0. And if that voltage is 0, then the current through R24 must also be 0. Well, think about that. I got a current coming in here. Here's a node where it can split. This current's 0. So all of this current must be going through R21. So the current through R20 and R21 must be the same. We've already figured out that the current through 20 and 22 must be the same. And again, 22 coming into this node, if there's no current here, the I22 must be the same as the current through 23. So this current is the same as this current. Now, what does that tell you? Oh, wait. Well, R20 and R21 are effectively in series. They have the same current. And the same thing can be said about 22 and 23. They have the same current. They're effectively in series. Yeah, I know there's a thing here, but there's no current going through it. So effectively, they're in series. Well, if that's the case, then this combo is 2K, and this combo is 2K. Now we got a 2K that's effectively in parallel because they're both connected to this point and this point. And like I said, we can kind of ignore this because there's no current through it. So that pair of 2Ks, or effective 2Ks, must be 1K. So I've got 1K for this and 1K out here, so this must split in half, meaning V out number 2 must be 5 volts. Let's go check. Bring my probe over here. All right, so yeah, it is 5 volts, and notice that we see 7.5, 7.5, right? So if I come in here and look at the current, that shows up as 0 amps. 0 volts, 0 amps. All right, current through R20, 2.5 milliamps. Current through 21, 2.5 milliamps. And notice 2.5 volts on each. Same thing over here, 2.5 mils, 2.5 mils. All right, beautiful. Now, how does that compare back to where we started? Let's think about that for a sec. Just because of the way the circuit is built, it must be the case that the current through this upper run of 3 resistors, R1, R2, and R3, must be the same as R7, R8, R9, that current. Why? Well, again, it's the symmetry, right? You could rotate this thing around this central axis and swap 1 and 7, 8 and 2, 3 and 9. Now the question becomes, all right, if that's the same and that's the same, that means the voltage drops, in other words, the drop across R1 and R7 must be the same, right? The drop across R2 and R8 must be the same. The drop across R3 and R9 must be the same. Well, what about the current going through here? Do we have a different current through here? I mean, there's nothing about the symmetry that says, just looking at it, this current's got to be the same as this. Okay, and then, what's happening with these resistors? Is current coming in, out? What's going on? Well, let's just sort of do a little mind kind of daydream experiment here. So, you've got a current here and you got a current here, and they're the same. All right, let's just suppose the current through R4 is a little bigger. I don't care how much bigger, 10% bigger, 50% bigger, but it's bigger, right? That's all I care about. It's a little bigger. What does that do? If this current is a little bit larger than these two currents, then this voltage drop must be a little bit larger than these two voltage drops. That means, right, this point here, this node here, and this node here must be at the same potential because, again, we said these currents are the same and these resistors are the same. But if this current's a little bigger and this voltage drop's a little bigger, that means this node voltage here must be a little closer to the ground than these two. All right, so, just to throw a number out, maybe this is 8 volts. That means this is 8 volts. Maybe this is 7.5 volts, right? Because this is a slightly larger drop. Well, what does that mean? Well, you're going from a higher potential to a lower potential. So there must be a current flowing down through R10 and up through R12, right, to balance that out, right? So you're going to have a drop plus to minus and another drop plus to minus that compensates for the fact that this R4 drop plus to minus is a little bit bigger, right? Kirchhoff's voltage law, this drop plus this drop has to equal this drop. And then when we look at this, right, Kirchhoff's current law has to work out. So when I have this current coming in and a little current here and a little current here, that has to sum to a somewhat bigger current going through R5. So what does that mean? That means the R5 drop has to be even bigger than the drop across R4. So when I move over to this node, guess what happens? Oh, by the way, these currents are going to be a little bit smaller, right? Because we lost current through here. So these are a little bit smaller. This is a little bit bigger. This makes the situation even more pronounced. In other words, this node here is going to be even closer to ground than these two nodes, which will also be the same, right? This voltage and this voltage will be the same. But this thing is going to be even closer to ground. So what does that mean? Again, we're going to have currents through R11 and R13 that are going to add and produce an even bigger drop across R6 and a smaller drop across R3 and R9. But that can't be because these three resistors all wind up at the same point. You can't have a bigger drop across this than you do across these and come up with the same voltage if this voltage over here is actually lower than these two voltages, right? There's no way that could possibly work. And you could do the experiment the other way. You could, mentally you could imagine, oh, this current's a little bit smaller. It doesn't work. You're always going to get to this point and find out that you have a violation, right? It's a wire. This is one node. It can't be three different voltages. So sort of by process of elimination, this current going through R4 has to be the same as the current through R1, which has to be the same as the current through R7. If that is the case, right, these three voltages are the same, these three voltages are the same, these three voltages are the same. And as we saw in the hint, that means the currents through these vertical resistors, R10, 11, 12, and 13, must be 0. So I can ignore them. Pull them out. There's no current through them. There's no drop across them. Pull them out. What do you have? 3 1Ks in series, basically. 3 1Ks in series. 3 1Ks in series. So you've got 3K that's effectively in parallel with 3K that's in parallel with 3K. 3 3Ks in parallel is 1K. 1K, 1K, it's a 2-to-1 divider. So, you get half of the potential. Bingo, should be 5 volts. Let's see. Well, there's our 5 volts, and we'll take our probe and look around. All right, so I'm getting 1 2/3 volts across that, 1 2/3 volts across that, 1 2/3 across that. We should get the same as we go, as we go through here. Now, you might at some point find something is off by just a tiny little bit due to, finite precision in the calculation engine here. These currents should all come out to 0 with 0 volts. All right, so 0 volts, 0 amps, 0 volts, 0 amps. All right. Okay, so we're getting crazy tiny thing. All right, so this is the little carried error I was talking about, right? Look at the value of this current. It's 8.88 times 10 to the minus 19th amps. All right, I think we can call that 0. I think we can safely call that 0, right? Okay, so that's kind of cool. Just looking at it, you wouldn't notice that, but, this is the way it works out. And our hint was helpful. Is that where it ends? Well, not if you know me. Because it gets crazier. Consider the following. If there's no current through these resistors, right? This is the original circuit. Except I've put in like wacky values for the vertical resistors. If there's no current through these things and there's no voltage drop, then the value of the resistor doesn't make any difference. It could be anything from 0 to infinity, right? You can rip it right out, which we saw, right? We just ignored them. But you could put other values in there, right? 1K ohm, 7 ohms, 22K ohms, 5.4 megohms, anything you want, and it's still going to work out the same. How is that for neat? Look, there's our 5 volts. And again, we can poke around here, right? There's the 1 2/3 volts that we saw last time. And again, you know, we might see some tiny little trailing digits here because of precision. Oh, look at that. We got a current of just about 1.6 times 10 to the minus 17th amps, right? 15 point, let's call it 16 femtovolts. Ooh, femtovolts, right? Yeah, I think we can pretty much ignore these resistors. So you can put in any resistors you want in the vertical position, right? Or leave one out, right? Leave two out, you know, so you can like freak out your buddies here in your circuits class and give them something like this. It's like, hey, figure this out. Boom, right? Is that all there is? Of course not. It gets even better. Check this out. It turns out you don't have to have all the horizontal resistors be the same size. And you're not stuck, by the way, with 3x3. So, you know, you could do 3x4. You could do a 5x7. I've got a 4x4 here. All right. Looks kind of weird. So the first thing I'm going to say is, if you do this correctly, once again, the vertical resistors, and I've got 9 of them in here, will not make a difference. So I've got values ranging from 7 ohms up to 5.4 megohms, right? And it turns out none of these values are going to make really any practical difference, okay? And you'll notice that in these rows, right, these resistors are changing size. 1 1/4 K, 2.5 K, 5 K. Vertically, they're changing, right? 1 1/4 K, 625, 312.5, 416 2/3. How's that for a nice round number? What the heck is going on? Well, it turns out for this system to work, right? If you think back about the original hint, the idea was, if I could say the voltages across the pair of resistors was the same, the end result would be we'd have a 0 differential voltage across one of those vertical resistors. So all I really have to do is make sure that the voltage across this sort of vertical ladder, right, these 4 rungs on this ladder, I just have to make sure that these all get the same voltage. And the same thing would be true for these 4, and the same thing would be true for these 4 and these 4. But this voltage does not have to be the same as this voltage. And this voltage doesn't have to be the same as this voltage. So here's what I've done. The first section going across is the same. 1 1/4 K, 1 1/4 K. Then I just decided to double it. So let's go to 2.5 K. And then I decided to double it again, 5 K. So as long as I keep this same ratio, in other words, a ratio of 1 to 1, 1 to 2, and 1 to 4 on these other horizontal runs, everything's going to work out. So I go 625, right? 1 to 1. Double that, 1 1/4. Double that, 2.5. Come down here to 312.5, right? And I just happen to be, you know, for fun, I'm just cutting them down half this way. So 312.5, 312.5, right? There's the 1 to 1. Double it, 625. Quadruple it, 1 1/4. Now, why is this row, you know, kind of like weird? It is still 1 to 1, 1 to 2, and 1 to 4, right? Same value, double it again. I use these values just so that this whole thing would work out to 1K. That's the only reason why, because I want to get the same result that I started with. So the easy way to do that is you figure out, okay, look, these are all going to be in series. So this is like a 10K, and you know, this is like 5K, and this is 2.5K. And I just have to find the fourth combo that when I put them all in parallel, I get 1K, right? So you can just figure out the conductances, right? 10K is 0.1 millisiemens, and you just work your way back, adding up the pieces until you get to 1 millisiemen, which is, 1K, right? So let's do an analysis. Hey, look, got 5 volts at the output. Big surprise there, huh? Okay, so coming across here, I got 625 millivolts, 625 milliamps. Notice how the milliamps have doubled up. Still 625 millivolts. Again, we're getting that little tiny error at the end. And here it's a little more obvious because I can't do exactly 2/3 or 1/3. So this is going to produce a little bit more deviation, but still tiny. They're all 625, and then if we came over to here, it's a volt and a quarter. 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 Okay. And over here, it'll be twice that size, 2.5, 2.5. All right. And if we go and look on the verticals again, these are going to be, again, close to 0, ideally 0 volt and amp. But again, okay, we're getting picoamps for this one, picovolts, tiny values, right? Nanovolts, picoamps, as you start poking around here, right? Okay, but ultimately, again, partly because I can only get 6 digits on these things, so it's not going to balance out perfect, but theoretically you could do it, all right? So you can play games with this, right? You can make some like impossible circuit, right? It just looks like it's insane, but keeping these things in mind, it turns out this is actually quite simple to solve. Would you notice that up front? When we came, back here, right? Would you notice that up front? Yeah, maybe not. I mean, if you just threw it down, in all honesty, if you just gave this to me before I thought about making something like this, I would probably say, yeah, well, I'll do a mesh analysis. Looks pretty easy. Once you've done mesh analysis a million times, yeah, laying out the equations. It's like I said, it's a bit of a grind. You would just do it. But it's kind of interesting. You think of what the rules are, the circuit analysis rules, and what they imply. Certain things work together, KVL, KCL, the voltage drops, all these things. And you discover some really cool things, right? And this is a useful thing to actually, even though this circuit itself is probably not super useful, the idea that you could have identical potentials on either side of a resistor and therefore have no current and voltage through and across that resistor, that by itself is actually a very useful idea, right? We use that in bridge circuits, like for measurement devices and things. So it's maybe not as arcane and odd as it might first appear, but it's a nice way to stretch your brain out, right? Okay, well, we'll see more of these in the future. And until then, this is Professor Fiore saying, have a good one.